Pop quiz. Which situation has higher entropy? Gas confined to one small region? Gas spread through the whole room? Or are they equal? Lock in your answer. We will reveal it soon, and by the end, you will know why. In this video, you will learn what entropy really means, how to picture it on the microscopic scale, and how to estimate entropy change in simple physics examples. On the microscopic scale, entropy is related to how many accessible microscopic arrangements, called microstates, are possible for a system. More accessible microstates means higher entropy. Fewer accessible microstates means lower entropy. You may hear entropy described as disorder, but that shortcut can mislead. A better idea is that entropy increases when energy or particles can be distributed in more ways. That is why heat tends to move from hotter objects to colder ones. For the combined system, the energy has more accessible ways to be shared. Let's build the main model. Imagine a thermally insulated container with a wall in the middle. At first, an ideal gas is trapped on one side, while the other side is empty. If the wall is removed, the gas spreads into the larger volume. On the microscopic level, the key change is not that the particles want chaos. It is that the larger volume gives them far more possible positions. Since the spread out state can happen in many more ways, entropy increases. Now let's answer the pop quiz. The gas spread through the whole room has higher entropy. Why? Because there are vastly more ways for particles to be spread out than for them to stay packed into one small region. This also explains why free expansion looks irreversible. In principle, particles could all drift back into one side by chance. But for a macroscopic gas, that is so unlikely that we never expect it to happen on its own. For this isolated system, the higher entropy state is overwhelmingly more likely. A great example is melting ice. In solid ice, water molecules are held in a crystal structure. In liquid water, they can move and rearrange more freely. That gives the liquid more accessible microscopic arrangements, so its entropy is higher. So far, we have covered the big idea of entropy, why gases spreading out increase entropy, and why melting ice raises entropy too. Ready to lock it in? Tap the link for study guides and flashcards on this topic, so you can keep learning without missing a beat. We can also measure entropy change. For a reversible heat transfer at constant temperature, the change in entropy equals reversible heat transfer divided by temperature. More heat transferred gives a larger entropy change, while a higher temperature makes the same heat produce a smaller entropy change. The word reversible is important. For irreversible changes, we calculate entropy using a reversible path between the same initial and final states. During melting, we often use a handy version of that idea. The entropy change equals mass times the latent heat of fusion, divided by temperature. This works because the ice absorbs latent heat while staying at the same temperature during the phase change. Let's do one example. Suppose 1 kilogram of ice melts at 0 degrees Celsius, which is about 273 Kelvin. For ice, the latent heat of fusion is about 3.34 times 10 to the 5th joules per kilogram. Remember, temperature must be in Kelvin. First, write the phase change formula for entropy change. Next, substitute the mass, latent heat of fusion, and temperature. When you calculate it, you get about 1.22 times 10 to the 3rd joules per Kelvin. That positive value tells us entropy increased during melting. Here is a common error. Thinking entropy only changes when temperature changes. That is not true. During melting, the temperature can stay constant while entropy still rises because heat is absorbed as latent heat and the molecules gain more accessible arrangements. Now transfer the idea to heat flow. If a hot block touches a cold block, energy moves from hot to cold. The hot block loses entropy, but the cold block gains more entropy than the hot block loses. So the total entropy of the combined system increases. Here is a fast method you can use on problems. First, identify the system. Next, ask whether energy or particles spread out more. Then compare how many microscopic arrangements are possible before and after. Finally, decide whether delta S should be positive, negative, or close to zero. To recap, entropy is related to the number of accessible microscopic arrangements. Gases spreading out and ice melting raise entropy because particles or energy become less constrained. And in simple constant temperature cases, you can estimate entropy change using reversible heat transfer divided by temperature. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.